the number of repairs in a cable. It depends on what they are. And it's up to the registered mine electrician on where he wants to use that cable. If you had 3 or 4 full splices that were down in the reeling area all the time, you would, or near an anchor point, you would probably want to make sure that you didn't have it there. There's a couple of things he can do. He could end for end the cable, cut the plugs off, refit them end for end the cable if the other end of the cable was quite good. He can take it out of service and use it as an auxiliary cable somewhere else. He can cut out the bad part and add in a new section if he wanted to, one complete new section, if he wanted to. So anywhere you see on these cables where there's been a repair, that's the repair from the Australian standard that you're looking at on the board up there. That tells us exactly what the repair is underneath the outer sheet. At one of the classes where we were at, we had a particular person tell us that the reason that the pilot wire or the earth continuity wire was through the centre here was so that if you did stretch the cable and it busted, it'd break that small wire first and drop the power off before these main conductors parted and created a flash. It's not. There's one here that we've got. It's got the white phase and the blue phase completely pulled in half, and all of the 3 earth wires pulled in half. We've got the red phase which has started to pull out, and it's obviously broken down here, and hanging right in the middle of it, which is still intact, is that little piddly pilot wire right in the middle. We have to make sure that the cable is completely symmetrical at all times, which means that there's no out of balance between the phases inside and the earth system that's inside. Now, if any of the earths get broken in these cables, you can still have a single earth wire, for instance, still connected to your machine, so you have an earth down there. The only problem is the other earths build up voltage in them due to the induction from the other phases that are in there. So you can have a rise of potential on the actual frame of the machine, and particularly on shuttle cars where we've got rubber wheels. But we have to do a test to maintain within the Australian standard that we have enough earths in the system to be able to carry the fault level down there. I suppose at home there your wife might have been washing up at the sink at some stage and she's put a hand in the water and said, oh, I've got a shock off that. You guys have gone up and put your hand in, you can't feel anything. The reason for that is that your hand-to-hand contact between you and earth is a lot higher because you've got hard-worked hands, whereas a housewife hasn't. Her resistance is lower. Depends on your health, your physical well-being, your psychological well-being, etc., etc. But that's basically, in rough terms, what that means. If you are finding that that's happening, you've probably got something wrong with a main neutral or something in your system somewhere, and you should get it checked out because the voltage is rising on the earthing system within your house. Now this fella here is supplying you 11 kV supply underground. It's constructed of a certain manner as well. It's got this outer sheath, which is a PVC sheath, and we also have to test that to make sure that there's no cuts or holes in it, because it is actually protecting everything that's inside here. One of the mines we were getting these cables in that had 20 and 30 cuts through them. When we investigated to find out why, we found out that everybody at the mine was issued with a Stanley knife because the guys never had 10-foot long arms so they could reach up and cut the tyres. They were jumping and having a slash at them, and not only cutting through the tyres, but they were cutting through the outer sheath at the same time. So it's important that we maintain this outer sheath for the full length of it. It's a PVC sheath. It's a bugger of a thing to repair. We don't like repairing them, do we? Bugger of a thing to repair. But that's what it's there for. Now underneath that, we've got this steel wire armour. This is called a PLSWA cable. It's a paper-lead steel wire armoured. Underneath we've got the steel wire armour that's underneath this outer sheath, and then underneath the steel wire armour we have this bitumistic hessian, for a better word. Now underneath that bitumistic hessian we've got lead. Now that lead is in one continuous pass, one continuous tube throughout the full length of the cable, and the reason that bitumistic hessian is there is to protect the lead and to stop the steel from abrading on it as well. Now underneath the lead, on the inside, we've got 3 conductors, 11,000 volts. Those conductors are wrapped in paper. They're not wrapped in any sort of insulating material like we have here, like this rubber. They're wrapped in paper. The important thing to remember about this is that the paper is impregnated with a special insulating oil. Around those 3 conductors, there's paper wrapped around the whole lot as well, which is also impregnated with insulating oil. The thing here we don't have inside here is any earthing like we had in those other cables. We don't have the 3 earths going through the middle, and we don't have any semiconductive material. So we have 3 phases sitting tightly knitted closely together. Now if you crack this lead open for any reason, if the lead cracks open, this oil will gradually find its way out. It doesn't run out, it's not that thin, but it can work its way out. We found it on the outside of the cable in many instances. So once the oil starts to run out of these papers, they start to dry out. Once they start to dry out, the resistance to the voltage inside reduces, so that means you can get a flash. Now because you've got 3 phases sitting closely together, the worst thing that we can have occur is a phase-to-phase fault, which is normally what happens with these things. So it's important we don't crack this lead open. Now the reason the lead cracks open is because it's bent too sharply, the cable's bent too sharply, or the plug's not handled correctly at the end. We normally find that the damage is done within the first metre, metre and a half at the back of the plug is where the damage is normally done, if it's not in the plug itself. And it's because the damage has been done to the cable from being bent too sharply. You bend this stuff too sharp, you're stretching the lead on the outside of the arc, and you're starting to make it ripple up on the inside. You're creating air voids. The thing that you don't need in this cable is to have any air voids between these phases, and that's exactly what occurs, and that's where we get problems, when we get air in there. This particular plug here was on the surface just up from the portal at an underground mine, and it had been in service for some time, and one afternoon shift about 5:30 in the afternoon, there was a fault occurred in the back end of the plug down inside here. When it occurred, the pressure was so great inside that it blew the complete back end out of the plug. It snapped these 2 half-inch bolts off that are here and left the heads in the back of this section, and it blew this section about 4 metres away. It blew all the doors of the substation open, and there was a box full of electrical prints about 3 metres away, and the substation caught on fire. So you can imagine how much energy was there. This was supplying the whole of the underground mine, so what we call the fault level was very high, extremely high. It put out 2 underground mines in an open cut until they could clear it. So you can see the potential there for a hell of a lot of damage to be done. Completely snapped those off and blew it out through the back end. Now these are very heavy, these things, and where the damage occurs is usually within that section there, because the plug end isn't handled very good. You should have a minimum radius at the back here of about 1.5 metres, I would suggest, at the back end. That's where the damage occurs, and that's where you start damaging the lead and the papers. If you bend it too sharply, the papers inside will crack open. And if they crack open, you've got a good chance of having a face-to-face fault. This particular part here sits in there, and that's why that's shaped like that, because there's a set of clamps, lead clamps, sit in the back underneath this cone here that hold that mechanically tight, also supply good earthing medium for the full length of the cable. When we got this one in, we found that the problem was in the plug, so we chopped it off, pulled it out, and then the guy doing the repair cut it off back here, and when he did, we found that that was completely broken off, so the lead is completely broken off all the way around in that section. This one here is due to the IMCO slamming it into the roof. Now in the past, there's been quite a few of these at the mines. The potential to have a great flash there is higher than most of the other sections in the mine. We found in that report that's going around that the IMCOs are starting to overtake the miners as far as faults go. Shuttle cars have always been to the fore, followed by miners, then by IMCOs. In that report there, over 4 months, there's been more IMCO damage than miners, but the shuttle cars are still to the fore. This particular piece here, you'll notice there's a sharp cut around it when it comes around. That's only where we ring the lead to break it off, to remake the plug off. That's all that's there for. When the guy made it off, when he first started to do that, he noticed that there was another mark there, so he peeled it back a bit further, and you can see a complete fracture right through the lead in that section, and that's in the back end there. And this piece here that I've got, if you have a close look at it, it's getting a bit dirty now from getting handled, but if you roll it around, you'll find that you've got stress fractures right down the side of the lead on one side. Just this particular cable, as I said, they're updating the equipment that they're using on these, the insulation, the sheaths, the actual technology of the thing has gone ahead in leaps and bounds. And this cable here is more or less a replacement for that one there. So physically it is lighter, but physically it's a lot bigger to look at, this thing. And it's a lot stiffer. And that's because of this new improved insulation. This one's a 22,000 volt cable, this one, by the way, that I've got there. And they make them in what we call a single core variety, which is like that. And power stations are starting to go to these now. They're doing away with their lead armours. And most power stations don't use a 3-core one like that. They use 3 single cores like that one there.
The first sign of overheating is seen when the neoprene sheathing becomes polished and assumes a darker, glossy appearance. It is important to remember that even if power is cut off, the temperature can continue to rise for 30 minutes or so until it reaches ignition temperature.
What's wrong, Harry? Lost power. It's your cable, Harry. You'll have to change it.
As soon as oxygen reaches the hot-sealed inner layers of cable, there is imminent danger of ignition. Experience proves that a normal fire extinguisher will dampen down a fire by sealing off the cable from oxygen, but only temporarily. It has little effect in reducing the heat of the inner layers, which will again ignite. Water alone will effectively cool the cable to a level where the fire will be extinguished and will not restart. Any ignition, particularly in the flame-proof area, could immediately ignite any gas that could be present and puts the entire mine at risk. This hazard can be greatly reduced by ensuring that no more than 2 complete layers of cable remain on the reel when the shuttle car is at the miner. Also by improving ventilation of the reel compartment. Safe cable practice is the joint responsibility of the section electrician and car driver, as well as the deputy. Should a car get bogged, the cable should ideally be removed from the reel before an attempt is made to free the shuttle car.
In slow motion, you can see how the devastating buildup of heat in only 1/3 of a second blasts molten copper in all directions. This massive heat buildup and explosion was entirely because the fuse links were replaced with copper links. Nothing else was changed. But look at the damage. The entire center phase of the horizontal bus bars has been destroyed, together with most of the outgoing bus bar copperwork.
In recent years, major resources have been devoted to enhancing safety and reliability in low and high voltage switchgear. But despite the fact that modern switchgear is much safer than previous designs, the risk of an arc occurring can never be entirely eliminated. The most usual causes are faulty handling by erection and maintenance staff, the human factor, overheating, weakening dielectric strength and insulation, and mechanical defects due to insufficient or incorrect maintenance. An arc rapidly gives rise to a very powerful increase in pressure. At 10 kV and a short-circuit current of 40 kA, the pressure in the vicinity of the arc rises to about 15 tons per square meter within 10 milliseconds. The temperature of the arc increases violently to 20,000 degrees and causes a heat blast. Simply expressed, the energy released from the arc is equal to the square of the current times the duration. The elevated temperature causes a cable fire after about 100 milliseconds. After 150 milliseconds, copper burns, and after 200 milliseconds, sheet steel as well. The disconnection time upon an arcing fault can be as much as 500 milliseconds. Of that time, about 400 milliseconds is the relay and communication time, and the remainder is the circuit breaker time. The material damage to the switchgear will then be very extensive and can lead to long periods of breakdown. A person exposed to an arc runs the risk of incurring very serious burns.
High-power fault in a switchboard can be lethal, as this controlled test at Testing and Certification Australia so graphically shows.
There's a guy in the States, he was working for one of the electricity boards over there. I've got the video at home. And he got caught on a switchboard, and he was kneeling down at the time, and the current went up his arm and went down through his body, and it blew out through his knees. It blew a hole completely through his kneecaps all the way through. It burned all his arm up to the shoulder. It burned all of the muscle out of his left leg there and the calf. And he was in hospital for quite some time. He lived. But for 3 weeks, they kept on opening his arm up and cutting out the cooked meat inside, because it kept cooking over 3 weeks. They were trying to save the arm on him, and they couldn't. Finally, they took it off, and he's got a prosthetic arm there now. He fingers and all, operates with the muscle in his neck here and his left shoulder. And he goes around there training and showing these videos. But while he's in hospital, they took photographs of these operations where they're cutting out all this cooked meat over the several days, which is shown on the film. It's pretty bad stuff. Wasn't meant to be a trick question. The reason that we throw that up there is that our minds only perceive what we want to see, and the point we're trying to get across is that cable has been down there ever since we've been doing underground mining, and we see it and we pay no attention to it. We see something like that, and our subconscious mind only relates to what we want to see out of it. So what we're trying to do is say, look fellas, in the future, when you see that cable in a situation where it may get run over and you can relocate it with safety, relocate it. If you see that cable that's getting rubbed on some piece of machinery, if you can safely relocate it, relocate it. If you see somebody run over a cable and the power hasn't gone off, report it. At the end of the day, if the only thing you can do is report the situation, that's what we're trying to say. What's the first thing we do if we're told to go and unplug a cable? What's the very first thing we do? Make sure it's isolated. We're told to go and put a plug into this receptacle. What do we do? First thing. Sorry, can't hear. Okay, that's one. Any others? Any others? Make sure we've got the right cable. Make sure we've got the right receptacle. And number one thing of all, both times, make sure that the power is isolated. Just because there's nothing in there doesn't mean to say that that has been isolated. Always ensure that it has been isolated before you put anything into it. We've had a couple of incidences that happened where the pilot wire was connected to another circuit and the damn receptacle just happened to be energised. Okay, so make sure that it has been isolated before you remove a plug and before you put one in. When you come up to these receptacles, and you've all seen them, back to back is just two of these together, okay, on a frame. When you come up to them, first thing to do is to just try that receptacle and make sure that it's not wobbly at all. I mean, it won't be wobbly like that, but just make sure it's not loose. If it is, there's a chance that the bolts holding it could be loose. And if they are, you do not tighten them up. You get your section electrician to do it, because he has to come and ensure that the flame path gap on the back of this thing is correct. What a flame path is, it's a specified gap of a specified length between two mating metal surfaces of a flame-proof piece of electrical equipment. That's what it is. What is it there for? Okay, it's to cool down an escaping flame from an internal fault in the particular piece of equipment it's on. So by the time the flame gets to the outside, it's not hot enough to ignite gas or dust, as we saw before. It's of a less temperature than what we saw methane and coal dust was at. That's the idea of it. So as it passes across these two surfaces where they made, it cools down sufficiently. We had a deputy, I think it was the year before last, at one of the mines, was closing an isolating switch, and he actually got his hand burnt because a fault occurred inside and the flame went out between the two surfaces and burnt him. And somebody said, well, I thought it was supposed to be cool enough so it didn't do that. And I said, hey, you wouldn't put your hand in boiling water, would you, which is 100 degrees C? And they said, no. And I said, well, obviously it was hot enough to burn him, but not hot enough to create an external problem. So that's a flame path, that area there, and where that bolts onto is a flame path. So if it happens to be slightly loose, the electrician has to ensure that there's no grit or dirt down the back there, because you'll damage this flame path, and if you damage it in any way, then some of the flame could get out through that section and be hot enough to get outside to create a problem. So he's the one that has to do it, and he gaps it. You see him going around on various shifts with his feeler gauge, and he's going around checking those flame path areas to make sure they're not outside what the standard calls for. So that's that one. We have a look at the front of it. We have a look at the front. There's also another flame path here. Where you see that brass collar, for a better word, inside there, if anybody wants to have a look at this after, come up and have a look. But there's a brass collar sits inside there. It's part and parcel of this whole body. Where that's sitting is where the front end of the plug sits, which is one of these brass earth sleeves or earth skirts, we call them, is where that sits. So where that sits against that collar there, there's a flame path area. For today, we're going to treat the whole length of that as the flame path area on the plug, the whole length of it. Okay? That's also a flame path. Want to make sure it's not, hasn't got any deep scratches or anything in it. Also, we have a look up there to make sure it's not full of gunk. It needs to be cleaned out. If you've got any of these underground that do not have a dummy plug in them, or an indicating plug, or they don't have some sort of cover in them, then they should have. Because if you don't, you're going to get moisture in there, you're going to get stone dust in there, you're going to get coal dust in there, you're going to have a problem. You're going to damage the flame path and create other problems with the contacts. So we need to make sure that's clean. So they should be closed up one way or another. This is the earth sleeve or earth skirt, and we don't forget we said that was all the flame path of the plugs that you use in underground. The ones I've got here are 1000 volt, they're painted blue, and the red ones are 3300. There's a couple of different styles of plugs you can get. You can get them with a earth skirt or nose cone, some people call it, like that one there, or you can get them in one piece like that there. It depends on the type of plug that's being used. This one here has a mark right around the circumference of it. It's about close to 1.5 to 2 mils wide. It's very deep, you can feel it with your thumbnail. With all due respects to everybody, that one there would pass the test, because we've got a lot of length of flame path for a flame to pass over without creating a problem. However, when we saw that, and we don't know how it was done, we decided we'd keep it as an example, that particular one. I've damaged this one here specifically. I've put a scratch down one side, which you can feel with your nail. Now, if that scratch is running long ways along that flame path, then it probably does not comply, and it should be changed out. If you can't make the determination yourself, and just use common sense, if you can't make the determination yourself, see somebody who should be able to, like your electrician or your deputy or whoever, to make sure that they can make the determination. On the other side, if you turned over, I've put some indentations in the flame path with a hammer. They also don't pass, just to show you that there's a couple of different styles of things that can happen to them. So if the flame can hop, skip and jump up some of these little valleys, it could be hot enough by the time it got outside to create a problem. So I've damaged that one. The other thing is I've damaged the front end of this. A lot of these plugs that we get in, and I think Chris has found the same thing, people, if the cable's died for some reason, it's been cut in half, people pull the plug out and just go plomp and dump it straight in the deck. And as Chris said earlier, we get them in there with coal dust and muck absolutely chock-a-block jammed up to the front end. We've got to dig it all out of the front end of it. If you can let moisture and crap get on the inside of this, it'll go all the way through the plug and get into the back end, into the interior, which is one of these things here. Now that interior sits inside the plug there. The cables come in the back end of the plug. They get made off into what we call thimbles, and there's a landing in there where the thimbles sit up against, and then down through the front go the contacts and lock into the thimbles on this landing. So it's held in there fairly firm mechanically. If moisture gets in the front end there, it can go all the way through and get right through the back end, and you can see all the rusted sections in there, in the back end. The front end we can't get it apart. It's all rusted in there. All of the contacts are rusted and all the screws holding them. We have to throw that away, which we had to do with this. There's about $300 worth of equipment there alone without having to spend a couple of hours to remake it off again. A lot of money involved. So it's important that we have some sort of protection over the front end of these plugs if they're disconnected. Now, while these will let moisture in to some degree, it's a lot better to have something like that over the front end of these things than have nothing at all. If you can only put a plastic bag over it, again, if you can only put rag over it, you should have something over there to protect it. The main thing this here, as Chris said before, is to keep the mud and muck out, but also to try and protect that flame path a little bit if that's dropped for any reason. So it's very important that these are closed up. Okay, we've looked at the receptacle or the back-to-back, as we explained before. We have a look at the plug itself. First thing we do when we pick the plug up, we have a look around it to make sure that the flame path looks reasonable. And that one looks reasonable. It doesn't have to be highly polished so you can see your face in it. A lot of people think that the more polish you put on things, the better they are, but we get guys getting stuck into these with emery, and they actually wear down that surface so that that surface size there no longer complies. When these come into town, we have what we call go and no-go gauges that we measure that with to make sure that's within the Australian standard tolerances, is what it should be. We don't see this fella here, so we don't know when it goes back to the mine if the gap between that section there and the section in which you're putting it in complies. The only time these go off-site is when it goes away for what we call a Code D overhaul. So we have to measure these every time they come in. We also do a check on the pressure that's on these contacts inside with go and no-go gauges to make sure that we've got good contact on the contacts in here. Okay, so we look at the flame path on this thing. The next thing we do is look down the spout of it, make sure it looks all right and it's not full of crap. The next thing we do is just at the back end here, make sure that clamp's tight. I mean, you don't have to put a spanner on it, but it doesn't have to be loose. Just make sure it's firm. So that's the things we look at on the plug. When you look at the back of the plug, you'll find that there's a painted section on the cable where it comes out the back end here. That's for our convenience. It's called a witness mark. And when these cables come into town, one of the first things we normally do is have a look to see if that witness mark is painted all the way down to the neoprene cone that sits in there and clamps the cable in the back end of the plug. Now, if it doesn't, if we can see black rubber there, there's a fair chance that that's been stretched, that cable, and it's been pulled in the plug. Invariably, that's where we find the fault, is in the plug end. This particular one here is squashed flat on both sides. It was run over by a miner, and that's where the damage happens to be, is in there. So we've just cut it off and kept it. So that's the witness mark. All things being equal, we've made sure the power's off. We've checked and made sure this is firm enough. Looked up there, but it looks reasonable and clean inside. Flame path looks pretty good. No crap up here, no burnt pins. Away we go. Same thing applies to your banana plug. Exactly the same thing again. Flame path, interior, and the clamp on the back. This one here was pulled completely out of a machine. It's flashed. You can see all the burn marks inside it all the way through. And it's also broken the earth skirt on one side, completely snapped it off. This particular one here was on in a situation at one of the mines. Remember I said before how the contacts and the thimbles at the back are locked in to that interior, and at the back we've got the neoprene cone that sits right there holding the cable mechanically strong into the plug, and the plug's filled normally. The earth wires are made off onto little thimbles at the side here that have a screwed section in them, and they screw onto the side of the body of the plug. This one here is pulled completely out of the back end of a 300 amp plug, and it drew an arc out they consider was 1 to 2 metres long before protection cleared. It snapped off all of the screws and the holes that were holding these on and pulled these all the way through the plug and out the back end. So you can imagine how much damn tension that had on it. You can see where all the contacts are burnt on the front end there, where it drew the flame out with it. With these contacts, when you look at them, when you look down the spout, all you're going to be looking at is something like that. That's all you're going to be able to see. Okay? Now, they don't have to be bright and shiny, but if you have a look at some of these that I've got here, you'll see where the front end of them is either damaged or badly burnt. You won't see that tinning on there. The tinning has disappeared because of the heat generated in there. Now, these things have got a spring around these fingers. These are split fingers go down these contacts, and they've got a spring around the end of them. The spring's there so that when the male pin goes in there, it maintains pressure on the male pin and contact so you don't get any burning in there. If that spring's damaged in any way, and how it gets damaged, if water gets in the front end of the plug, it starts to rust the spring. When the spring starts to rust, then you don't have as much tension on those fingers anymore. So there's not as much contact pressure on the male pin, so it starts to heat up. Once it starts to heat up, it's like a dog chasing its tail. It then heats this up. Once it heats that up, the spring deteriorates further, and so on, until you get to the stage where you actually get burning down the inside of the contact altogether. And if you have a look at those, you'll see where the contact's actually burnt off. This particular one here never had a spring on it when it came into us, that one there, which we salvaged. On this one here, you'll find a little bit of burning on this tapered section. This little tapered section here, where it goes in the front end of the plug, it comes down onto the female contact that's in the back, and it goes up on the tapered section and locks. Some people have been changing the screws in there at the mine sites, and they haven't been using the correct length screw. It's been too long. So it's been pulling the female one up, or screwing down in the female one at the back and bottoming out before it actually puts them together and makes a good connection on the taper. So you start getting burning around this tapered section. You also get burning on the screw that's holding it if it's the wrong screw, and all the current will go up the screw and burn the screw away. That one there has got half the spring washer missing, and you can see where half the thread section is missing when I pass this around here. So it's important that the correct length screws is used. I had one here at the last sitting we had, which we don't have anymore, that had a hole blown completely through the side of this contact. When it blew a hole through it, it also blew a hole completely out through the side of the plug itself, completely out through it. The mine concern still has that plug. I haven't been able to get hold of it. And I did have the contact, but she's gone missing. Thank you very much for your attendance. And we like questions from the floor, and we had quite a few this morning, which is good. It's not much you're sitting there and not getting anything out of it. If you only go away with one thing from today, well, that's a bonus as far as